Hello. In this presentation, you will discover FindTextualAnswer, a new function in the Wolfram language that appeared with the version 11.3, and which is about answering your questions given a text or a collection of texts. First, you will have an overview of FindTextualAnswer, what it is about. Then you will see some practical uses of it. And then we will talk a bit about how it is implemented, because what is interesting is that FindTextualAnswer is mostly based on deep learning approach. And deep learning is a trendy and very promising field of artificial intelligence. And now it's notable that the Wolfram language enables you to easily play with deep learning methods and artificial neural networks to build this kind of high-level applications. So what is FindTextualAnswer about? So it's a new tool in the suite of text analysis in the Wolfram language. It's about reading comprehension, so understanding a text with a machine. And it's about natural language processing, which means that it takes inputs that are text and that are just written in English. You don't have to care about special formatting. You can speak natural language. And the functionality is question answering. So we are going to give a piece of text in English and a question also in natural language. And FindTextualAnswer, the goal of FindTextualAnswer is to yield the most probable answer in the text given the questions. So let's take this short example. We give a sentence: Paris is the capital and most populous city of France with a 2015 population of 2 million something. And how many people live in Paris? And it will give you the piece of text that most probably answer this question. So it's similar to text cases. So text cases is about also extracting some kind of information in a text. For example, with the same sentence, you can ask to extract all the numbers and it will give you them. But with FindTextualAnswer, in this context, you are just interested in one number and you are able, with the meaning of the question, to express in which number you are interested. But also, FindTextualAnswer can cope with a wide variety of questions. So to illustrate that, I took this little paragraph about the weather forecast in some region in Russia and asked several types of questions. So you can ask what is the temperature. You can also ask us for the time, when, so some location, some numbers, some distance. I asked several questions. Then FindTextualAnswer is able to cope with a list of questions. Then here I'm threading over the question and the respective answer, and FindTextualAnswer is almost right. So what is the temperature in Yakutia, for example? And it gives you this piece of text here that answer this question. And the same for all the questions. For example, where is Yakutia? And it's extracting you this Russia here. Okay, so FindTextualAnswer can be perceived as similar to Wolfram Alpha, which also answer your question, but actually it's a very different technology and also the application is different. In Wolfram Alpha, it's based on a carefully curated knowledge base that is a unique stuff in the world. And here you are going to be able to provide your piece of text where you can find the answer. So you can use any customized source of text. And for example, you could imagine that you want to find the answer in your history of email. So you could provide to FindTextualAnswer your history of email and ask your question, knowing in advance that the answer will be in your email, and FindTextualAnswer will find it, hopefully. And now let's see the options and all the arguments of FindTextualAnswer. So the first argument is the text, or a list of texts. The second argument is the question, and then an optional third argument is the number of answers that you want to have. You can ask for several possible answers. So in the current example, if you ask for 2 alternatives, it will just give you the 2 numbers that are possible population for Paris. You can also, with the first argument, ask for some properties about the answers to know where they come from and to have more context, for example. So here, for example, we are going to ask for the probability that the answer is correct, the string, which is just what we already had before, the position in terms of character in the in the text, and the containing sentence with the answer highlighted. So if we ask this on the current example, we have two answers. So it's a list of two lists, and then you've got the probability, the string that answers, the starting and ending character indices in the text, and then this is the containing sentence with the answer highlighted into it, which is practical to have more context about what is this answer about also sometimes. Concerning the output structure of FindTextualAnswer, so the design is similar to the one of ImageIdentify for those who know this function. So if you only ask one question about one text, FindTextualAnswer will give you just a string. But if you ask more questions, or if you use the third and the fourth argument of FindTextualAnswer, it will return you an array whose rank and dimensions depends on this dimension for the second, third, and fourth argument. So let's illustrate this. If I have a text and I ask two questions, then it will just return me a list with two answers. Okay, then if I use the third argument now to ask for each of these two questions that I asked two answers, then I will have a list of lists with the first question, the two answers to the first question, and then the two answers to the second question. Now, if I asked a list of, this was the same as asking just the string of the answer. It will give you the same answer. And now if for the last argument I use a list of properties, then it will be an array with an additional rank. And so the first question will come first, with then the first answer of the first question, and then all the property, the string, the probability here, and the containing sentence. Okay, this was for the API of FindTextualAnswer. Now let's see some practical applications of it. So as I mentioned in the beginning, you can use any kind of collection of text or text that you have. So here I took a mixed example when you can give a mixture of the result of a text search in local, for example, an explicit file, and a Wikipedia page. And you could give also some URL. And then here it's about the US Constitution. I'm asking what kind of crimes are punished, and asking for 5 answers. And then given all that text that contains some of them which are not relevant for the question, like the origin of pieces, the FindTextualAnswer is going to filter and to give you only the relevant answers to your questions. Then a convenient source also to look for is Wikipedia, because it's a refreshed knowledge source where everybody participates. So yeah, it's an encyclopedia that is always moving. So it's convenient for FindTextualAnswer. So for example, you can search for all the pages that talks about the Sagrada Familia. Then with Wikipedia data, you will extract all the contents of these pages. So all this title, any one of these titles, so it will become a big string. So here I don't display the string, but we can count the words in them and see that in total we have several thousands of words in which FindTextualAnswer can search the answer to one of your questions. So for example, who built the Sagrada Familia? Here I ask for 5 answers, and the probabilities and their containing sentence with the highlighted sentence. So I have the column of probability, and then comes the answer, and we can see that Antoni Gaudí, the real architect, is coming first. And you can also use word cloud to nicely display your answer. So word cloud is usually natural text processing when you want to display some information. When you've got words and weights associated to words, then word clouds are totally appropriate. And in this case, the size of the words is representative of the probability that the answer is correct. So here is all kind of possible answers. I ask for 20 at the maximum, and then when the aggregated probability of all this answer, Antoni Gaudí will win and is leading the answers. And we should mention also that when you use Wikipedia search, you could directly feed your question into the search. And for this, in the previous search, I was using the title here, looking only at the title of the Wikipedia pages, but here you can search in the content directly for your question. And then, yeah, the Wikipedia search will already select some Wikipedia pages that can answer your question, and then FindTextualAnswer will give you the precise answer, like who founded the Who, and you have here the 3 members of the Who that founded the band. Okay, then now concerning the timing, so yeah, FindTextualAnswer, if you give a big collection of text, it can take a significant amount of time, but we should mention that if you have a graphical card, then it can be much faster, because FindTextualAnswer is based on neural networks, and the neural network can benefit from parallel computation from graphical cards. So if you've got a compatible GPU, then you can specify it with the option target device, and FindTextualAnswer will provide you the answer much faster. So now let's look a bit at what's inside the FindTextualAnswer, what's under the hood. So FindTextualAnswer is in 2 steps, basically. If you give a big collection of text, first FindTextualAnswer will filter them to select several dozens of text, of passage, paragraph that possibly answer your question based just on statistic of words. So it's looking at the words of the question in the passage. And then in a second step, we are going to do a more computationally expensive operation with neural networks to precisely locate between the paragraphs the answer and assign them some probability. So concerning this first step of FindTextualAnswer, filtering a significant number of paragraphs in order to have just a few dozens of paragraphs with several hundreds of words each, we use the TF-IDF approach. So TF-IDF means term frequency inverse document frequency. And in this approach, you first have a big piece of text. So you have a predefined corpus, then you can define some feature extractors. So here I show how to do it with the Wolfram language of TF-IDF. And then in this representation, each word within the paragraph will correspond to one component of the representation, and the term frequency is the number of times the term occur, and it will be penalized by an inverse document frequency, which means that the common words will have a lower weight, basically. So all the stop words will have quasi a null weight, and the TF-IDF will focus on the good words. And then you can compute, given this principle, the similarity between, for example, your question and a set of sentences or paragraph. Here I used the sentences, so I have got a corpus, I split it into sentences, and then if I sort all the sentences with a cosine distance based on this TF-IDF representation, I will see that comes first the one that contains the word of my question. So I was asking, what are the horns of a rhinoceros made of? And then in the first sentence, I have got horns and made. I don't have rhinoceros, because actually in my corpus was all about rhinoceros. So rhinoceros is judged as a common word and weighted less by the IDF term. Okay, and then in the second step, it's about a neural network that, given some paragraph, which are typically 300 words long, no more, it will precisely find the possible answer to your question and assign a probability to it. So it's a neural network that does it, and that was entirely designed and trained and deployed using the Wolfram language neural networks framework that I highly encourage you to have a look at. And this is a graph of layer that corresponds to a network. So the network, we have in total 78 layers. Each layer is like a function that takes as input a tensor, so either a vector or a matrix or a list of matrices or a tensor of higher rank, and that's also output a tensor. And among these layers, there are some non-linearities, and there are some layers, some linear layers, for example, with some parameters that are going to be learned or trained, which means that they are going to be tuned to some database to fulfill some goal, to minimize some loss functions. So in these architectures, for example, the brown squares represent layers that are learned that contain parameters. Okay. So the input of the networks are a list of tokens of the question and the context. So a token means either a word or a punctuation mark or any other symbol. So for example, here we have this question, what color are elephants? And we have this text, elephants have a gray or white skin. Then the tokens will be the list of words, elephant have a gray or white skin, and the punctuation marks. And there is also another vector which indicates which words of the questions are present into the, which words of the text are present in the question in any form. So for example, here the word elephant, it appears in the context and the question. So here there is a vector with 3 values which indicate, okay, elephant is not present in the case insensitive case, but if we ignore the case, it's present. And if we ignore the syntactical form, it's also present. Okay, and this is just an additional feature to cope without vocabulary. Yeah, because in this kind of models, as we're going to see, they are based on a dictionary of words where they map words to a vector that is represent the concept of the words, but the lexicon that you use is always limited. And for example, if you use the name of a person that is not very famous, you won't have it in the dictionary, but if you ask a question on it, then maybe this word is important and you have to indicate to FindTextualAnswer, okay, if you find this word, it's important. Okay, and then when you apply the network to this kind of inputs, then you will have an output association that will give you the probability of the start and the end position. So that means for each token of the input, it will indicate you whether it has the chance or not of being the end and the start. And there are some activation, we are going to talk about them later. So if we visualize it, that's it. In the green curves means represent the start, the probability to have the start position here. So there is a high probability that the start of the answers begin at gray, and a high probability of that the answer ends with white. So probably the good answer will be gray or white in this case. Okay, now let's go maybe a bit more into details and see what's the architecture of this neural network, because it was a neural network that was really kind of tailored for this application. So it can be like this, split into 3 big steps. First, it encodes the context and the question into some intermediate representation. Then there is a step where we are matching the information, both so it's a 2-way step. We are going to match which information for the context is relevant for which piece of the question, and which information of the question is relevant of which piece of the text. And then there are going to be a decoding step to end up with some probability that the answer will start or end at a given position. So here in this notebook, I won't have time to explain everything, but those who are interested can look at it. And but I will insist maybe on the word embeddings, the first step. So the word embedding is mapping the words, which are symbolic inputs, into vectors that represent the concept. So for example, if you give some kind, these three types of words, and here I have a word embedding models that were trained on Wikipedia and GigaWord, a kind of language model, then it will map into a space where you can separate the concept, you see. So finally, this first step here is getting the concepts behind this word, but independently for each word. Whereas in the second layer here, we have a recurrent layer where the output at a given position will depend on all the words that become before and after. So here we are going to also understand the semantics, but in context. So to resolve the ambiguity, for example, if you have an ambiguous word, depending on the context, it will choose the concept of the words. Then we have a two-way attention mechanism. When first we are going to reinterpret the question given the context. So each word of the question is going to throw attention at the context and to give a new representation. And conversely, the context is going to throw the attention at the question. And in the end here, we are going to have a representation of the context that is given the question. So that is taking the question into account. And then we are going to have, again, some bidirectional recurrent layers that finally provide the probability of the answer to be right, to be at a given location. So in conclusion, we have here a new natural language processing function that is based on state-of-the-art neural networks. There is a link to a blog here where you will see what I tell today in form of a story. And it's important to underline the fact that the technology is different from the one of Wolfram Alpha. So it is a new technology based on neural networks. And here I insist that there was a great improvement in the neural network framework in the version 11.3 that enabled us to design this new application. And I highly encourage you to have a look at this framework, which is incredible to make new kinds of application. And there's going to be more and more similar functions in the language that are based on deep learning. For example, for now in the vision domain, there is already image identify and imagery style, and we are working on many others. So more and more application like this will be released in the future. Thank you.